Okay, so let's get started on our chapter on nuclear energy. In the United States, nuclear power has been a controversial issue for more than a generation. Internationally, nuclear power has achieved greater acceptance, with Western Europe and Japan now generating much of their electricity from nuclear energy. Here we have is a graph that shows the worldwide nuclear energy production and percentage share. So as you can see, these on the y-axis we have the terawatt hours of produced electrical energy worldwide by nuclear, starting from 1971 up through I think it's about 2007 here, and you can see that there has been an increase over time. We're going to be taking time in this chapter to look at fundamentals of nuclear energy. We're not going to dive super deep into it, but the idea is to give you a concept of how nuclear energy works, and we'll touch upon fusion towards the end of the chapter. So, an atom consists of a heavy positively charged nucleus with much lighter electrons in orbit about the nucleus. Since the atom is electrically neutral, the number of protons is equal to the number of electrons. And the masses are as follows. We have the mass of a neutron being 1.008665 atomic mass units. Proton is approximately the same, and electron mass is significantly less. The proton and neutron are the particles that make up the nucleus are called nucleons. By convention, the number of protons in a nucleus defines what is called the atomic number of an element, and the sum of the neutrons and protons in a nucleus is defined as the mass number. So the usual notation for an atom is you have the element X has it in such a way so that the atomic mass number is located on the bottom left subscript, and the mass number is located in the upper right superscript. Isotopes basically are equal in proton number, but the isotopes would have different number of neutrons. Thus, for example, uranium. Let's look at uranium. So uranium has the same number of protons, but the total number of protons plus neutrons is different. So these would be called uranium isotopes. Since up here you can see that the mass number is different. So we have uranium-238, uranium-235, and uranium-234. An electron is often represented by this notation. And a neutron, which carries no charge, can become basically N, with the, again, the bottom left-hand side is the atomic number. So the atomic number would be 0, but the mass number would be 1. In a chemical reaction, whole atoms are involved, but in a nuclear reaction, the reactant nuclei do not show up in the products, but other nuclei or different isotopes of the reactants are present. So consider a nuclear reaction involving elements A, B, C, and D. And notice how the conversion of mass, and atomic number is maintained. So what about this reaction? Right, you can see on the reactant side and product side, if you were to do the math, you would find that for the reactants, you have 33.984141 atomic mass units, and the products is 30.7. 0.45525 atomic mass units. In this case, you can see that mass was not conserved. The product mass is less than reactant mass by an amount of about negative 3.24 atomic mass units. That represents the amount of mass that was converted to energy. So how do you quantify that? Well, you would quantify it as the change in energy of a converted mass would be that converted mass times the speed of light squared. So in this particular case, you can see if I were to go ahead and take that from that reaction, right, we have a negative 3.24. That would be the change in atomic mass units multiplied by the speed of light. After some conversions, I would find that I had a amount of energy that was converted from mass would be negative 3,000 mega electron volts. So when Z protons and A minus Z neutrons come together to form a nucleus, energy is emitted. This energy, called the binding energy, comes from the conversion of some of the mass of the neutrons and protons. The mass of the resulting nucleus is reduced from the mass of the individual neutrons and protons by the mass equivalent of the binding energy. Excuse me. Three types of nuclear reactions are important in the production of energy. We have fission, fusion, and radioactivity. In fission, a heavy, basically one with a high atomic number, a heavy element is split into two or more lighter nuclei. In fusion, two or more light nuclei are fused to form a heavier nucleus. And radioactivity occurs when an isotope spontaneously undergoes decay or disintegration into a different nucleus, usually by emission of one or more smaller particles. Currently, all large commercial nuclear reactors utilize fission. So in fission, neutrons are the only particles that can be practically used in fission reactors, and only a few isotopes are fissionable by neutrons. Nuclides that undergo fission when a neutron is absorbed by the nucleus are called fissile. Consider two fission reactions involving uranium-235. We have on one reaction here, uranium-235 and a neutron will yield xenon, strontium, and two neutrons. And the second reaction takes uranium-235 and a neutron and yields barium, krypton, and two neutrons. These two reactions result in two different nuclei from the uranium, and of course two neutrons. So if this reaction is to be sustained, more neutrons must be emitted than absorbed. So the idea of a chain reaction, right? So you have one neutron yielding two more neutrons. So you must have more neutrons being yielded than reactions. Let's look at a quick example here. It says compute the energy resulting from the following nuclear reaction where uranium would yield two neutrons, with one uranium-235 with one neutron would yield xenon, strontium, and two neutrons. So to get started here, you can see we have the atomic mass of each of the products and reactants. If you were to go ahead and do the math, you would find that the total change in mass between the product side and the reactant side would be negative 1.98 atomic mass units. And if you were to go ahead and do the conversion from that mass to energy, take the atomic mass change multiply it by the speed of light squared. And then, of course, you need to take into account all your conversions, which I'm not going to include in this slide. In this case, you would get negative 2.963 times 10 to the 11th joules, or negative 185 mega electron volts.